All right, here's where we're looking at the second presentation for ELCM374, and we're calling it Introduction to Wide Area Networks. So in this presentation, we're going to define 5 basic components of communications. And previous to this, we essentially addressed the physical elements like the DTE, the DCE, and the medium involved. And now we're going to add the data elements that that are necessary for connection to work, or a network connection to communicate real, meaningful information back and forth. Explain the differences between industrial and business networks. We're going to find that there's not a whole lot of difference in the equipment and things like that these days based on Scada and industrial networks adopting the internet. But there is some specifics that we do want to discuss and talk about. Then the next thing is to outline something called the OSI network model, and this stands for Open System Interconnect Model. And this is a model that's applied to all networks, and specifically network or internet communications. And we'll talk about that in a little bit more detail. Any network course I've ever been on seems to bring in or refer to or talk about the OSI model to introduce students to what that's all about. So part of that will be discussing communication protocols, and then we're going to review binary and hexadecimal number systems and the conversion between binary and hex and decimal and hexadecimal and so on, because as we start working with some of these data protocols, the information that we know is all ones and zeros is most often shorthanded into a hexadecimal number system so that it can be communicated easier when we're talking about the values of those ones and zeros, and therefore knowing how to do the number systems conversions efficiently is something that we want to do when we're understanding the information that's being communicated. All right, so that's where we're going here. So as we mentioned before in our previous presentation, data communications is simply the transfer of ones and zeros, and that is transferred over some type of connecting medium. Could be an unguided medium like wireless, or it could be cable, as in coaxial cable, or twisted pair cable, fiber optic, and so on. So when two computers, or two terminals as we know them as DTEs, so this would be a DTE here and a DTE here. Remember, the DTEs are the source and destination for the data. They terminate the data and decode it as a receiver. They assemble the data and send it as a transmitter or a sender. Now here we're taking it a step further and saying, besides the medium that connects these two terminals, we also have some other elements, right? And one of them being the actual, what is being sent, what's the message? That's part of the necessary part of this connection as well. So if we look at that then, quite simply then, the sender is who is talking. The message, what is it that's being said? So contained in here, what we know, that's all ones and zeros, but the thing is, what is it that is being communicated by those ones and zeros? Well, within the message, what defines the meaning of those ones and zeros is something called the protocol, or the language. And I tend to take it a step further and just call this the data protocol. Because what we need to understand is there's really a difference between a data protocol and a physical protocol. We've been talking about RS-232. RS-232 is a physical protocol. So RS-232 is a physical protocol. And because it's a physical protocol, it's defining things like cables, pinouts, max cable lengths, voltage levels. So what is the voltage level for a logic 1 or a logic 0? and so on and so forth. It's a physical protocol defining those parameters. But the thing is, is that's the vehicle or the medium by which the ones and zeros are being communicated over, as you could think of it as a pathway or a road between the sender and receiver. But then there's the message that is represented as ones and zeros, and then further a language to interpret it, and that is what would be called the data protocol. The data protocol has to be applied to those ones and zeros in order to give them meaning. So one way to think of that is maybe a simple telephone call, in that if we look at a telephone call between two individuals, there's certainly the physical protocol is the same if you're using the telephone, right? So the telephone lines and connecting through the central office to another person on the phone. The physical protocol is the phone system there, or what's called the plain old telephone system, and that's actually an acronym that is used lots. Plain old telephone system. That's describing the physical protocol, but the language that's being spoken is describing a way of thinking of the data protocol. So if you're talking to someone else who's Italian and you're in English, you have a data protocol that's a mismatch, and there won't be communication. So you have to have a common language or data protocol. So both be Italian or both be French or English and so on. So that's what I'm going to be commonly referring to as the data protocol riding on the physical protocol. Okay, so then we have the medium, and of course we've talked about that before. So what is it? Wireless, wired, fiber. So this is kind of a review in that we've talked about how computers or microprocessors are in just about everything these days, and as long as we have a communications port or a way of connecting to a common bus or network with that communications port, we could build a communications network of which these devices, these microprocessors, these smart devices could share information. And I think I mentioned this term before, but if I haven't, let's just bring it in. This will be used in a lot of curriculum and documentation you see on networks and industrial networks, and these are called Intelligent Electronic Devices, or IEDs. So it's really just what I've referred to as a smart device before. So yeah, we can do any of these things here when we connect them together. We can work on any one of those tasks or jobs. So an industrial network is a network of smart devices. So in the list you would find things like, of course, computers, PCs, terminals, HMIs, human machine interfaces, RTUs, that's one specific to Scada, and so I'll be using that a lot going forward as we get more Scada specific, but that's a remote terminal unit. So that RTU could be defined as a Scada network's remote communicator. Communicator. Its primary job is to communicate with all the local area components in a substation or generation plant and so on, to communicate with all the local devices using their specific language or protocol, using their specific mediums or physical protocols, and collecting all that data and then reporting to a higher level, or the master, or the MCC, the Master Control Center. Because remember, Scada networks are all wide area networks. So that's really the job of an RTU, to do that. So, and we'll certainly be talking about the role an RTU plays in more detail. So then we have PLCs. PLCs can obviously be part of an industrial network and part of a Scada network as well, because like I mentioned before, PLCs can be configured such to do the job of an RTU. And that is to simply fully feature them for communications, and as opposed to discrete control or analog control. They can be doing entirely communications and acting as an RTU. So PLCs, and then just in a general term, IEDs. So you could really say that all of these listed up here could come under the classification of IEDs. So when we're looking at industrial networks as opposed to a business network, an industrial network tends to operate in high noise environments. There's, because of instrumentation, because of control, because of all this automation that's going on within these networks, there tends to be a high level of electromagnetic interference, crosstalk, and things like that that need to be considered when you look at both designing, installing, and putting together these networks. There's high security requirements. You could say that's a higher level security than in most businesses. You know, if you take, for example, maybe government stuff, that's a little bit different. But if just your average, local business would tend to have lower, or would see their data is probably somewhat less of a security risk. Whereas when we're talking about our water treatment plants, our nuclear power generation, our substations, and things like that, certainly we can see that security, preventing any kind of hackers, break-ins, and or intrusions is something that's really important for the safety of us all, and when it comes to that type of thing. All right. We have real-time requirements. So remember in a Scada system where the central operators and engineers at a master control center like ASO need to make well-advised decisions on how to operate our grid, they're looking for real-time data. That is to say, statuses of breakers, switches, currents, and power values and voltage values as a virtually what would be ideal is a instantaneous value. So there'd be no time delay in what's being read and what is there in reality, and that's called real-time data. So in the Scada network, that's something that's always ultimately important, is to have real-time data and not have what's called latency in your data, where it's showing up at a time really too late to respond to it properly, I guess is a way of putting it. We're always looking for what's called in Scada a snapshot of what's happening over a wide area. And a snapshot would be a picture of everything at that moment, at that time, a real-time snapshot. So, we're really looking at standards for variations within an industrial network, which would be quite different than when it comes to a business. Okay, so manufacturing plants to oil and gas to water treatment to our electrical grid, water treatment, both wastewater and freshwater. You get the idea. And a review that Scada stands for Supervisory Control and Data Acquisition. Okay, so here we have just a kind of a pictorial diagram of a Scada network, and so there's no doubt by looking at this we should be able to, once we've had a chance to look it over, remember we're talking about a wide area network whenever we're looking at Scada, and certainly this is wide area, and because of that we've involved Data Comm here. So this is where our Data Comm over a long distance medium is going to be part of this connection. This central control station, or what I would often call the MCC, or the Master Control Center, is where all the Scada engineers for either a specific utility or ASO are looking at all their HMIs and looking at a real-time snapshot of their part of the grid, the whole grid, or whatever, to make decisions on how to control these remote locations and these remote devices that are part of a much bigger system like our electrical grid. So this is definitely going to be a wide area network. So everything that's occurring here is occurring over the cloud, or a wide area network. So in this example, it's really concentrating on a digital video server, but this could really just be a substation server which in Scada would be another way of really referring to an RTU. So in this example, they've seem to have concentrated on video, which is fine. Video is just another form of data that could be transferred as data files, video bytes or sound bytes, and things of that nature. But the idea being that it's data that's being collected from the substation at that local site as a local area network. And furthermore, there is a submaster, you could say, or a local master and an HMI that allows local maintenance people on site at the substation to really be looking at real-time data, much like the MCC is at the substation, where the local area networks and its devices are being monitored for specific data and displayed as objects on your HMI. Okay, but then this is the local area network at the substation. Of course, that needs to interface with the wide area network, and it does that through Data Comm or a gateway. So this connection here would be called the gateway connection to the wide area network. So this is going to take you out to through a router to get you out onto the wide area, and at that point in time, that's where the data from the substations being communicated back to the MCC. So the central office or the central control station can have a picture of what's going on remotely at that site. So hopefully that gives you kind of an overall idea or bigger picture of how things are put together as far as a wide area SCADA network. So here's where we get a little bit more specific, and this is where we can apply some of the stuff that we learned in data communications. So first of all, when we look at this in network diagrams, it's very common when labeling connections within a local area network or a wide area network, we start by labeling that connection as the data protocol riding on a physical protocol. So I'll show you what I mean here in this example of diagram. Let's look at these. Notice how this is given the name RTU data concentrator. This is our remote communicator in our wide area SCADA network that's sitting at a substation, and let's just make sure we can point that out. This is the substation local area, but this is interfacing to the wide area, right? So again, what would we call this connection here that's over radio? This is going to be our gateway, isn't it? This is going to take us into the wide area. We're going to leave our local area network, which would be within the bounds of the substation, and we're going to hit that gateway and get out to the wide area network. So in this case, we actually have either two departments or two utilities monitoring the same location and possibly controlling a few things like breakers, switches, things like that. But there's two utilities or two masters. So you could think of this as MCC number 1 and MCC number 2. We can certainly have an RTU providing two roles. It can be a slave to a master for wide area network 1, and at the same time, simultaneously, it can be a slave to a wide area network number 2. Two different utilities, two departments, two different masters. Okay, and we'll be talking about that all more in detail when we look at specific master-slave networks or client-server networks and polling and things like that. But for now, let's understand that we've got that gateway connection from the local area, and it's the RTU that's communicating the information to the wide area. If we look at the at what's being shown for these two gateway connections to these two different MCCs, all that's being shown there is the actual data protocol. So we're not going to really study them other than making you aware of them, and you'll find them in a lot of our communications equipment. When we go to configure it, we'll find these protocols, but Conatel is one of them. It's an industrial network protocol. And another one is ELCM374, both data communications protocols for wide area network applications, right? And so even though we don't study them, if we just can understand both of these to be data protocols, we know that those are the protocols that would be listed here in our connection, but we're missing in this diagram the physical protocol. So if we take something that we have studied so far, in some detail anyways, a point-to-point connection here between a port on the RTU and a port on this radio, this wireless radio, we could use a point-to-point physical protocol, and that one being RS-232. RS-232 we know is point-to-point. So we could have an RS-232 cable connection there, and what are some of the things that, from what we've learned, we'd have to keep in mind? Less than 15 meters length, right? Because now we're working on the physical protocol side of things. Less than 15 meters in total length. This would have to be a straight through connection, and it would have to be straight through based on what? Based on the fact that we're connecting to a DCE, right? Wireless radio is the one that takes the signal from the terminal, highs and lows, which we know is the same for all terminals, and changes it to a signal appropriate for the transmission medium, which in this case is radio. It would have to change it to an RF carrier to send out as a wireless connection. So we know when we make that connection from DTE to DCE, we need to use the straight through cable. Okay? So now we could label that and say Conatel over RS-232. Conatel is our data protocol, and it's riding on our physical protocol, RS-232. Okay, so if we look at the next example, LNG8979, another example of a wide area network communications protocol for industrial networks, but we haven't defined the point-to-point connection here. And in this case, let's just go with Ethernet. Let's say that we went with point-to-point Ethernet here, connected a straight-through Ethernet cable from an Ethernet port on the RTU to an Ethernet port on the DCE, or the radio transceiver, being able to transmit and receive. And so that means that what defines our maximum cable lengths of that Ethernet are 75 meters. That would be a straight through cable. It would be pinned out as an Ethernet connection is, and so on and so forth. So the Ethernet is the physical protocol that's defining that connection. Okay, hopefully that makes some sense. So now this is our wide area network connections, right? This is what connected this RTU back to the MCC. Now, if we look at this RTU, it's taking on the name data concentrator, and I might as well talk about that right now. And that is to say that when it comes to RTUs nowadays, because they're in environments where the sensors that are picking up all of their variables for analog data like voltage, current, temperatures, pressures, and all that, the sensors are smart sensors. You'll find that there's not a whole lot of discrete input loops, or DI connections. There's not a lot of AI, or 4 to 20 milliamp 4 to 20 milliamp connections, where there's hardwired field loops that are being digitized or interpreted by the RTUs. And that's simply because the sensors, the devices that are in these locations, are smart devices. So as an example, if we've got a protection relay that's monitoring line current, why would I connect a 4 to 20 to monitor that line current as a field loop to the RTU, when I can simply, through communications, ask that smart relay for that value that it's picking up by a CT or a PT, and report that value back to the MCC as a value that was collected by data communications, as opposed to reading it as a field loop. So that's where RTUs these days are primarily taking on the name data concentrators, because they're not reading they're not digitizing those inputs, or I/O. They very rarely have I/O connected directly to them these days. They're simply communicators for the local area and the wide area, and they're picking up all of their variable data through the use of communications. And that's what we have going on here. So instead of a 4 to 20 for connecting to these spots, it's a communications connection. So if we take a look here, this would be a local area connection, a LAN connection to a data communications protocol for this local area called Modbus. And we'll be looking at Modbus in more detail, as you know, in this course, if you've looked at the course map. So this would be a Modbus connection that we can clearly see as a multi-dropped connection, right? So on this multi-dropped connection is where we can clearly identify that this couldn't be RS-232. Being RS-232 would mean that would have to be point to point. We can see this is multi-drop, so this would undoubtedly have to be a multi-dropped physical protocol. And an example that we've looked at that was multi-dropped was a asynchronous serial connection like RS-232, but RS-485. So this is where we could say that this is Modbus over RS-485, which would give us multi-drop. Okay. Down here is where we have another protocol we're going to be looking at in the last half of the course, DNP3. And let's just pick another multi-dropped network down here, and we'll call it Ethernet. So we know we can multi-drop Ethernet just like we do on campus in the lab. And so that's an Ethernet connection. Therefore, we would look at maximum cable lengths of 75 meters and so on and so forth to connect our system. And we would have the RTU now speaking DNP protocol over Ethernet to gather data from these devices. And then when it came to the other network here, we'd have a Modbus message or protocol being used to communicate with the recloser and the smart meter here. So that's just a general overview of what this, what that would look like as a specific Data Comm physical protocol for a substation. Just picking up where we left off here. So yeah, that's going to be kind of an overview of a network at a substation, and how the RTU is involved as the remote communicator for the wide area network, and some of the description of the connections that make up those networks, both on site and to the wide area. So when it comes to a business network, we tend to have a little bit different equipment, but the network itself nowadays is really not a whole lot different. And I mentioned that based on the fact that SCADA networks have adopted the internet. They trust the security now, they trust the reliability, they trust the speed and performance to give them real-time data. And so as a result, we find that it means the network equipment is really pretty much identical from business to SCADA networks now. The only difference being is, you could say, the quality of the equipment is built to a higher standard. So if you think of Ethernet switch in a business network, most likely it's going to be, could be found almost anywhere, like Best Buy or Memory Express or any of those suppliers. Whereas when it comes to Ethernet switch within a industrial network, you would be looking at an industrial grade Ethernet switch with built to higher standard, higher approvals, more testing, and military spec components, higher temperature ranges, vibration resistance, and all that sort of stuff, which of course pushes the price tag up, but supposedly it's built to a higher quality standard. So, like it says here, a business network is a set of devices, switches, routers, hubs, printers, so on. And it says business networks are almost always connected to the internet. All devices on the network may be able to send or receive information from other devices on the network, because this is what's called a peer-to-peer network. So we've circled peer-to-peer here, because when it comes to how information is transferred over the network, how information is shared over the network, this is a primary difference. Even though the equipment is the same, the peer-to-peer is a primary difference. Each workstation in this network has equal rights to the network. And so when it comes to time to move data, we can have one of these workstations trying to access the common bus. Well, when it's trying to access the common bus to essentially say something or transmit something, it's an issue or a problem if another workstation, because it's a peer-to-peer hierarchy or a peer-to-peer setup, it can be a problem when we have two workstations trying to access the network at the same time. And this is where there's protocols employed in a business network and peer-to-peer to handle those situations with different protocols like CDMA and things like that. But the idea is that in a peer-to-peer protocol, collisions or data collisions are part of what's accepted. It affects the real-time retrieval of data. Because of these collisions, it slows things down. They need to be sorted out and figured out in order to carry on with the transfer of data and so on. So in a business network, workstations within the network are operating peer-to-peer, which is definitely much different than an industrial or SCADA network specifically, where data collisions can't be tolerated because of the way it could result in the loss of data. It could result in a greater than accepted latency for that data being retrieved from a remote location. So peer-to-peer would not be set up for a SCADA network. So there's industry standards for the networks, off-the-shelf equipment, like even from retailers like Best Buy and things like that. The networks are dominated, the business networks are obviously dominated by Microsoft. There's no requirements for real-time, meaning that if it takes a while to download some data or if it takes a while to get some data, it's not considered crucial to the operation or the process. And there's a higher, it's more prone to, or less security when it comes to business networks. And again, of course, it's user focused. So it means that any one of those workstations in the peer-to-peer at the time they want to access the network, they become the master. They become the number one until such a time as you could say they're beat out and or overridden by another workstation. So that's the way you could say it in a peer-to-peer network. It's user-focused. So when it comes to network design, we really have these three categories that need to be considered for designing a network: performance, reliability, and security. And you can kind of think of it this way, in my mind anyways, when it comes to business network, many times in general, it's focused this way. So it starts with this being number one priority, number two being reliability, and three being security. And when it comes to Scada, it's generally kind of the other way around, where everything's about security. Our greatest nightmare in Scada is that we have unauthorized access, and it causes destruction, loss of life, damaged equipment, outages, loss of revenue, and so on and so forth. And then second to that is the reliability, where we have an outage in terms of communication and can't get a snapshot of what's going on at that site. And then lastly is really performance, and that's because really in terms of the amount of data that's being moved with respect to the high-speed connections that we have these days, it's not very demanding as far as performance goes on our networks these days, because of the small amount of data that's actually moving in most Scada networks. So it's kind of like top down for business for that list, and bottom up when it comes to Scada. So what do we have when it comes under network performance? Things that affect network performance, of course, your hardware, the software that's running. Is it efficiently using that hardware, or is it poorly designed software that affects performance? So you have hardware, software, the transmission speed, what's it capable of in terms of what's the equipment and the medium capable of for bits per second. Number of users is a big one for a business network in particular, where if you have everybody on the system at the same time, peer-to-peer, workstations all trying to access the network simultaneously, that's going to definitely cause more data collisions. It's going to have to involve more organization of who gets to access the network when and for how long and so on. And so as a result, it definitely affects network performance. Reliability, this is where we look at failures. We look at the recovery time. Scada networks are regulated for recovery time as to what would be the case for a failure and how long would it take to recover from it, and catastrophic recovery as well. So all of this is something that's number two on the list when it comes to industrial Scada network is its reliability. Number one, and probably last for a business network, is our network security. And I think I mentioned this before. If you were to look at any Scada training course these days, just go onto Google and look at Scada training. There's one topic that would be in common for 90% of the training and seminars that you would see for Scada, and that is network security protocols. And so it's a big deal. And so there's certainly been a few situations around the world where Scada systems have been breached, causing issues and problems. And so that's a big deal, and it's something that's really a focus of Scada systems, Scada engineers, Scada development and design. So here's where we talk about something called the OSI model. stands for Open System Interconnections. And really, the way I start by trying to explain the OSI model is really, how did it come about? So when the internet first took off, it took off at a rapid rate. You know, everyone wanted to access a global a global network where information could be retrieved from all around the world. And so in doing so, it became a huge thing, I guess you could say. And so the way I look at that is, imagine you had a company that was just started between you and a partner. And then as the demand for your business started to grow, you would grow with it. And when you did, you would bring on more people, more departments. And as you went ahead, how would you make it more efficient? You would start assigning specific roles and responsibilities to those people that you've employed or that are in your company. And it's kind of the same way with the OSI model. The OSI model was used to break down or segment the internet communications into, I guess you could say, 7 different departments of what we call 7 different layers. So the OSI model is a 7-layer model. So it's got 7 layers. Now each one of those layers has a specific task or a specific responsibility. But the thing is that a layer, like say layer 3 in the OSI model, doesn't have to think about the whole job of communicating over the internet or addressing protocols or the rules for communicating over the internet. It only has to concentrate on layer 3 protocols, layer 3 responsibilities, and then also look at interfacing with the layer below it, which would be obviously layer 2, and the layer above it as layer 4. So when it's looking at designing, you could say, languages, data protocols, and progressing and tweaking its protocols, the only other people, the only other layers it needs to communicate with and address their protocols and interface with their protocols is layer 2 below it and layer 3 above it, as opposed to the whole pie, if you will, or the whole system. It's just the department above and the department below. So hopefully that kind of makes some sense as to why it was brought on board. And what it means is that hardware can align with all of this too. You can have layer 2 hardware, and the vendors or manufacturers that are building, designing layer 2 devices only have to concern themselves with 2 other layers. The layer 2 manufacturers only have to look at interfacing with layer 3 or layer 1. Layer 1 is actually the physical protocol, so this means that this device would have interfaces to physical protocol and an interface to a layer 3 piece of equipment. And then you can imagine vendors of layer 3, like routers, are required to interface with 4 and 2. So hopefully you get the idea. So when we look at the OSI model, we look at the OSI model from the, I guess you could say, top down, even though the top is given the number 7, so layer 7. So one thing to understand too is we can't arbitrarily assign these numbers to these layers. Layer 7 has a specific meaning, layer 6 has a specific meaning, and so on. In terms of any kind of, just so you know, in terms of any kind of tests or quiz as far as this goes, you won't be required to memorize this exactly. You'll just be required to do a matching exercise. So that is to say, if you had all the names of the 7 layers and the numbers beside them, all you'd have to do is be able to match the layer name to the layer number. When it comes to the functions, all you'd have to do is be able to match the function to the layer name. So as an example, if we said layer 7 is the application layer, match the corresponding function of that layer from the following list, the one you'd be looking to find to match to it is the one you see here. So hopefully that makes some sense. But we're still trying to understand this in a little bit higher level than that. So layer 6 is the presentation layer. Oh, sorry, just to back up, what does layer 7 do? It's the direct interface with the, I guess you could say, with the workstation. So what are some applications that connect to the layer 7 or that need to address layer 7 as a means of accessing the internet? Well, those are layer 7 applications like Chrome, Outlook, internet browsers, things of that nature. You could think of MS Messenger as simple application software using all layer 7 protocols and interfacing with them from the workstation or the HMI, you could say, or the human to layer 7. So that would be our application layer. Layer 6 is where we involve data encryption. We compress the data to package it to move over wide area network. And this is where we include translation software as well at the presentation layer, layer 6. Okay, layer 5 is the session layer. This is where as you have what's called a session up over a wide area network or the internet, you don't actually have a session that lasts from when you start a website or leave a website or communicate with a server and stop communicating with a server. There's actual multiple sessions that can be going on during that time, even though to you it seems like it's a single session. This is where layer 5 comes in to create those sessions, to set them up, and to synchronize them from one end to the other so that the session that you're on lines up with the session that the server assigns you. So then you have the transport layer. This is layer 4. It's for port addressing, segmentation, flow and error control, and this is where you'll find protocols that are doing that, that are in charge of looking after all of those roles. This is where you're going to find those protocols. Layer 3 is your routing and network addressing. So this is where you find your the device that is directing traffic based on a IP address. An IP address is a layer 3 address, and this is where your routers are using that IP address to route over the wide area network to the correct location. Now, as it goes through the network, it can encounter many layer 3 devices, and that's their job, is to route the traffic based on the layer 3 protocols that are being added to the message to get it to the right destination. So that's layer 3. And this is where you find routers. So routing and network addressing, or IP addresses, are found here. And you have your layer 2, which is your data link layer. This is where you find your switches, your hubs, your bridges, and this is where you find your network interface cards. So they're a layer 2 device. That takes you from a network interface card, takes you from the layer 1 of the physical layer is the cable or the wireless connection, and puts you into layer 2, where you have specific MAC addresses, layer 2 addresses that take you within a local area to the proper workstation. If you were to go from your local area layer to your wide area network layer, that would mean you'd have to involve layer 3, and you'd have to bring in an IP address to communicate outside of your LAN. When you're communicating within your LAN, MAC addresses are the way that the data finds its way based on a MAC address. So you have your layer 2. So this is where you find switches and hubs up here was layer 3. Now we have to involve IP addresses to carry you on through the network. Lastly is our physical layer, and again this is where we find our physical cabling, our RS-232, our multiplexers, transceivers, and anything regarding the assembly and representation of ones and zeros. So physical layer protocols would define voltage levels, would define maximum cable lengths and things like that. And as an example, this is where we looked at RS-232 as a physical layer protocol, and it defined all those things like voltage levels and cables and pinouts and ones and zeros for voltage and all that stuff. Okay, so when we look at a message moving this direction, what does it mean? It means you have a workstation, and let's just say this workstation is using, say, an MSN Messenger application software, and so it's accessing the internet, and the message that is headed out is just a simple hello message from this guy to the next one. Well, when this message is assembled using, say, ASCII characters or whatever, it's the job of the application software to package that using the application's protocols in a way that it's ready to hit the network, and then of course pass on to layer 6, right? So we've got layer 7 here. Now this hello message is packaged by the application layer with all the appropriate additional what's called overhead or ones and zeros that are corresponding to the application layer protocol, and then passed on to the presentation layer. Now it's at layer 6. At layer 6 is where the presentation layer looks after the encryption and compression in order to move it through the network efficiently, and after doing so passes it on to layer 5. I think you get the idea. Each and every time this message is being passed on through the stack, there's more ones and zeros being added, and that overhead is corresponding to each layer's protocol or information. So now we've added more information to that hello message from layer 6. We move to layer 5 for the session layer that's looking after the synchronization of the sessions and so on. We have to add layer 5 information. The message essentially is getting bigger. That started out only as a hello message is adding the overhead of all these layers. So you get the idea. You carry on. Transport layer, layer 4 is going to add more information. Layer 3 is going to add the IP addresses necessary and so on to move it through layer 3. Then you're going to finally get the information that is required within the local area network for the data link layer, layer 2, and then it's got to be sent out over the physical connection, whatever that might be, an Ethernet connection or whatever at layer 1. Well, once this is ones and zeros, this could simply be the 8-bit, well, it would be more than 8 bits, but just to give you an example, this could be the message that corresponds to hello within that package, but on either side it's being packaged by the other layers, right? So ones and zeros are what occur at the physical layer. Then you've got layer 2 information that's packaging this hello message. On the outside of layer 2, of course, is layer 3 that's packaging the data link layer message. I think you get the idea. It's like the layers of an onion being added on for all these layers. Once it reaches the destination over the physical layer, then these layers start to get stripped off one at a time to leave you with the overall message. So as we kind of open up this frame of this data, we're gonna strip off the ones and zeros from the physical layer, pass them on up the stack, and layer 2 is going to be stripped, layer 3 is going to be stripped, layer 4, layer 5, layer 6, layer 7, until finally all the layers of the OSI model that were used to move this through the internet, right? So this is the internet here that's connecting these two devices. Once it's moved through and removed all the 7 layers, you should at the other end be left with the hello message being seen by the by workstation B here. So notice how as we this is the analogy I just looked at. Notice how now we're adding on this overhead, right? So notice how this is the full package for layer 7 being passed on to layer 6 is the hello message, if we think of it that way. There's the hello message with the application header information is now being passed on to layer 6. Now notice as far as layer 6 goes, what it's taking is the hello message plus the application layer information and adding its header or its presentation header. And you can kind of see how that goes going on down the stack here. To finally, when you get to the physical layer, it's the whole thing. It's the hello message plus 7 plus 6 plus 5 plus 4 plus 3 in terms of the headers that are being added. And then it's packaging it with its layer 2 information on either side, and it becomes one big message where the hello is in the is the actual meaningful data that's being communicated. The rest of it, the ones and zeros, are all there just to get that package, if you will, or to get that message through to its proper destination over a wide area network like the internet. Okay, so hopefully that makes some sense. Now I am going to include a YouTube link as another explanation of the OSI model, just to help kind of maybe putty in some holes that I've left or whatever that that aren't gelling, and hopefully that'll help. But you can always go to Google and look more at OSI model explained and things like that to get a better idea of what we're talking about here. So on the receive side, you know, we're just going to do the opposite. We're going to start stripping layers off until finally we have that hello message being passed on to the workstation, the user, or the person communicating. So one thing to understand is, as this message finds its way through the internet, it's going to encounter many layer 3 devices. And if you look here, you can see that this is a message being interpreted or stripped down to the layer 3 information. And now it's this layer 3 device that somewhere within the wide area network is making the proper choice based on network traffic and things like that as to where to route it to next. Where is it going next based on the layer 3 information? And this is where specific protocols like link state protocols and things like that are operating on these layer 3 devices to say, hey, based on what I see for traffic on the network right now, this is the best route to get you through to the to where you want to go. And this is, of course, where we have our layer 3 router that looks at the IP addresses and what's available and routes them through by the best path, supposedly, to where they need to go. Now, that being said, it doesn't mean like every time you go to a certain server, you're picking the same path. It's these devices, it's these layer 3 devices that determine that best path, and that can change from, you know, minute to minute, day to day, because of traffic, because traffic's always changing. So this is where the internet's called a non-deterministic network, and it can't be mapped for every time you go from point A to point B. And that's why it's often shown as a cloud, because it's a non-deterministic network. And you don't know exactly how it got to where it's going, unless you use some of that software that will show you. But when you did use that software, you would see that it changes from moment to moment to moment, the way you get to your destination. So that's how come in network diagrams the internet is often shown as a cloud, because it's a non-deterministic network. Okay, so here's where we're just going to quickly talk about number systems and number systems conversions. A review of our data units is a bit is a single binary digit. Something called a nibble is 4 bits, and that's significant when we look at hexadecimal number systems, because it only takes 4 bits to represent all hexadecimal numbers. And then we have a byte, which is a traditional data unit for 8 bits of data transferred over a connection. So when we're looking at converting between binary and decimal and hex, it's something we need to review, and this is something you would have looked at in ELTR 232 in your electronics course, is number systems conversions. And we will review it with your calculator as well, because most of your calculators will do these conversions for you, which a lot of times can help avoid errors and things like that. So if we look here, we want to convert this binary number, which in this case is a total of 8 bits, or 1 byte, or you could say 2 nibbles. Okay, now that 8 bits could be broken down into 4-bit groups, where we'll learn later that each one of those 4-bit groups can represent a hexadecimal number, and therefore you can see why hexadecimal is used largely to communicate 1s and 0 patterns, because of how much easier it is to simplify that communication. So as an example, if I was to say the 1-0 information that I want you to know about is 10100101, it's easy for there to be a misunderstanding of what I said, or for me to make a mistake when I did that. Whereas if I represent those 4 bits as a hexadecimal value, which in this case would be hexadecimal number 5, and over here hexadecimal number A, I could simply say A5 is the value of 1s and 0s that I'm trying to communicate. And then once you took A5 and translated it to binary, it would be obvious the exact pattern of 1s and 0s I was trying to communicate. So as far as a binary number being converted to decimal, it has all to do with the weighting of each one of these bits, right? So if you were to look at, say, this bit right here, this bit here is in the 4th position, which corresponds to 1, 2, 3, 4. And so that means that bit is corresponding to the 2 to the 3rd location, or the decimal value of 8. So in this particular combination, there is 0 or no 2 to the 3rd weighted component. There's not an 8 component in that string. And so notice how here you don't see an 8 in those numbers. You only see a corresponding bit position and its weight wherever there's a 1 being added into that number. Okay, so we'll be practicing this in class and reviewing it with your calculators and so on. But this you can review and get out your calculators and go through a few examples. But this is how it breaks down. When it comes to conversion to hexadecimal, then, like we said, you take a long string of binary numbers and you break it into groups of 4, provided you know where to find the least significant bit. So as long as you know where to find the least significant bit of the code or the number, you can start there. You can work your way across, breaking the binary number into groups of 4, and then converting each group of 4 to a hexadecimal number. So 1010 converts to hexadecimal 9. You can put that in your calculator and check that if you want. 0011 corresponds to 3. 0010s to 2. 1101s to D. And you just have to understand that here, in order to convert that, that would be the 4-bit value of 0001. And when converted, that equals 1 as a hexadecimal or base 16 number. That would convert this long string of binary information to 1D239. Okay. Yeah, so then if you want to convert a hexadecimal number to decimals, you have to work the opposite way, where each one of these numbers corresponds to a power of 16. So notice how the least significant digit in that hexadecimal number is the 5, and that corresponds to 16 to the power of 0, and 16 to the power of 0 is 1, so therefore you have part of your overall quantity is 5 times 1. I'll leave that for you guys to review that, and you can do that as well on this slide, and we'll talk about that more in class.